Okay, thank you for the introduction and thank you for the invitation. I'm very happy to talk here. Okay. Okay, the title is Data Scientific Study of Kronecker Coefficients. And overall, what is a data scientific approach to math research? So in this approach, we regard mathematics as a study of data sets. Of course, mathematics is much broader and it cannot be simply a study of data sets, but we just regard mathematics as a study of data sets in this approach. And consider mathematical objects as data points. And then we generate data sets. Once we have data sets, then we can apply data scientific tools, including the machine learning methods. And then we can find the new structures, hopefully. And then we can make conjectures or prove theorem. After that, we can prove theorems, etc. So this can be the framework of math research. And then in this framework, we use a data scientific approach. So it has been, this framework has been applied to many areas, many topics. But the goal of this talk today is to present an example in representation theory. So that's today's goal. And then the title already has the subject. And then we want to study Kronecker coefficients using this framework or using this methodology. So the notation for Kronecker coefficients will be this. G lambda mu nu. So what is a Kronecker coefficient? So let us consider the symmetric group of degree n, or symmetric group of the group of permutations of n letters, and consider representations of the symmetric group over C. That means we have a group homomorphism from Sn to GLN-C, or equivalently, you may consider a Sn module. Then it is a well-known fact in representation theory that every finite dimensional representation is decomposed into a direct sum of irreducible representations, direct sum of irreducible representations. It's a very basic fact in representation theory. And the irreducible representations of the symmetric group are parameterized by partitions. And the notation is S lambda in this talk, and this is also usual notation because these modules or representations are called spect modules usually. I mean that's spect modules. The partition is partition of an integer is just the number of ways of writing the integer as a sum of positive integers. So if we consider 6, then just 6 is a partition, or 5 plus 1, 5 plus 1, or 4 plus 2, etc. Then the last thing is 1 plus 1 plus 1 plus 1 plus 1. So then these are partitions. Here we wrote these partitions as 6-dimensional vectors, but essentially the positive numbers are important, and then they make 6 as a sum. So there are 11 ways of writing number 6 as the sum. So yeah, these are partitions of number 6. And point is, yeah, S lambda is parameterized by partition. So each partition will give us one irreducible representation. So there are 11 irreducible representations for S6. The construction of spect modules, or the irreducible representations, is very well known. I will not go over the construction. And then now we can define Kronecker coefficients. Consider tensor product of two irreducible representations. Then this is the action of the group element is diagonal like this. Then this is a representation of Sn. It's a finite dimensional. So it is decomposed into direct sum of irreducible representations. And then we'll have the multiplicities of multiplicities of irreducible representations as nu. So that these multiplicities are Kronecker coefficients. The decomposition multiplicities are called Kronecker coefficients. So as you can see, every construction is very standard and basic. If you have two irreducible representations, then it's natural to consider the tensor product in many cases and for many reasons. And then Kronecker coefficients are nothing but the decomposition multiplicities. It's like taking the product of two primes, or like combining two elementary things. Then you want to decompose the product into the collection. Into the sum of the fundamental things. Of course, prime numbers doesn't make sense here, but some basic things can be combined, and then we decompose it again. Then we want to see the multiplicities. Okay, so my point is Kronecker coefficients are important and basic. Okay, that's my point. But they are difficult to calculate, and still we don't know much about these Kronecker coefficients. Individually, we can calculate these coefficients, but overall, we don't really understand the coefficients. But there are some standard facts about these coefficients. So let me talk about this. So if we have a partition like this, then length of this partition is L. So L is the last, number of positive parts. So, and then the number of parts is length. Then depth of this partition is n minus lambda 1. So lambda 1, the biggest part, is subtracted from n. Then that's the depth, d lambda. Then the first known fact about these Kronecker coefficients is that G lambda mu nu are invariant under the permutations of lambda mu nu like this. So once we have this one coefficient, or the permutations of the partitions are give the same Kronecker coefficients. So this is an elementary thing. And more non-trivially, we have this theorem. If Kronecker coefficient is non-zero, then the depths of the partitions, lambda mu nu, should satisfy this inequality. So this gives us some necessary condition for the Kronecker coefficient being non-zero. Some necessary condition. But this condition is not very strict. It's actually a very mild condition. So in order to characterize this, we need to have a lot more of information, or a lot more inequalities than this simple one. This is the simplest one, and this is a very mild condition. But many people studied this kind of a condition, but it turned out that a complete set of inequalities for this condition, G lambda mu nu being equal to non-zero, this is a complete set of inequalities is known to be intractable. So in principle, one may be able to write down the complete set. I mean, in principle, but if you really want to write that out, then yeah, it becomes more complicated. I mean, it becomes more and more complicated. So in the end, it becomes almost impossible to write down everything. So there may be some certain way, but there may be, but in practically we cannot see all the inequalities. So it's kind of beyond like the capacity of a human human being, and we cannot easily write down all the set of all the inequalities easily. So then natural question is, can you use a data scientific approach to determine whether this Kronecker coefficient is 0 or not? It's a natural question, because in some certain things, a machine can do better than humans. In particular, something is very complicated combinatorially, and sometimes we see better performance in machine learning. So there was the question one can ask, and then I also asked this question, and that was the motivation. Any questions so far? Okay, then we'll look at Kronecker coefficients using this data scientific approach. That means we have to generate data sets. So here, what kind of data sets can we get? And then we'll focus on the problem to determine whether G lambda mu nu is 0 or not. So we have to generate some data sets. So let us consider this set of partitions of n, and consider lambda as an n-dimensional vector. Already we did that. So to make it sure, if we have a partition of 6, 5, 1, and consider this as a 6-dimensional vector like this by putting enough number of zeros. Then this triple is a 3n-dimensional vector, naturally, because it's a triple. Now for each n, we have a machine learning problem. So it's simply this. So we have the set of 3n-dimensional vectors. And then from that set, we want to have a classifier, which gives us 0 or 1. So 0 represents the case when the Kronecker coefficient is 0, and 1 represents the case when Kronecker coefficient is non-zero. And clearly, this is a binary classification problem, and it's a very typical machine learning problem. Okay, that's the setup. Of course, if n is like 1 or 1, probably doesn't make sense. If n is 2 or 3, it's too small. But if n is big enough, then the data set gives us, I mean, the size of the data set becomes very reasonable. I will show you more details soon. And then after having the data set, we divide each data set for training and test with the 70% and 30% split. Of course, you can change these percentages. And then we apply nearest neighbors and convolutional neural network and light GBM. Light GBM is based on the decision tree algorithm. And then we perform experiments for n equal to 12, 13, and 14. Of course, we can do more, but soon yeah, it becomes very difficult because the size of the data set become larger and larger. And then in the architecture of CNNs, we put on only one convolution layer with 32 filters. So the design of this neural network is very simple. Very simple. It's not a complicated neural network. Very simple neural network. And then we obtained this result. So as you can see, the precision, I only recorded the precision. The confidence is also well, I mean, comparably high. So as you can see, nearest neighbor gives us about 93% of precision. And then CNNs gives us about 96 or 97% precision. And then light GBM gives us about 98% of accuracies. So it worked very well. It worked very well. So, and here there is a CNN2 and CNN3 that represent this small details. So we can feed this data point into the machine, or we may consider the data point as a matrix in this form, or we can put the data as a three-dimensional tensor like this. We can use this because the Kronecker coefficient is invariant under the permutations of the partitions. We may use this. Then we are enforcing the symmetry into our data set, or encoding the symmetry into the data set. And then actually that gives us slightly higher precision. But with these small details, so the conclusion is we have high accuracies. Okay, that's one conclusion. And immediately we begin to wonder how these high accuracies could be achieved. So then the one thing is that high accuracies means machine learning sees some patterns clearly. Otherwise, these high accuracies cannot be attained. So it motivates us to study further the structure of the data set. If we get like a very low accuracy, then there is no point for us to pursue this direction. But high accuracy suggests that it's very worthwhile and promising to do further analysis. So interpretation may lead some new structures or reveal some new structures. So in this talk, we'll use modifications of a PCA to understand the data set of Kronecker coefficients. PCA is, of course, a very basic method. So we'll do some modification of this PCA and study the data set. That's the next topic. Let me check the time. Okay. So for this, we introduce a few more notations. So the number of partitions will be written as a small p of n. This is the standard notation. So for example, p of 6 was 11. There were 11 partitions of number 6. And a partition is depicted by a collection of left justified rows of boxes in this way. So for example, partition 541 is depicted by these rows of boxes. The first row has 5 boxes, and then second row has 4 boxes, and the third row has 1 box. And this is a standard way of depicting a partition. And the conjugate or transpose of a partition is defined to be the flip of the original diagram along the main diagonal. The main diagonal is here. Then you flip, and that's the transpose of the partition. So for example, 5, 4, 1, and if you flip, then you obtain this diagram. And then this is the partition 3, 2, 2, 2, 1. And this is the transpose of this original partition. Okay, now there was a preparation. Now we define the main, one of the main objects. So let Pn be the matrix consisting of the partitions. So partitions. So rows are partition vectors. And then we define a matrix Yn using this equation. Pn times Pn transpose. And we'll call this matrix Yn the similitude matrix of the set of partitions, similitude matrix. And clearly, if you are familiar with the PCA, then you see that this definition is motivated by PCA. So we consider this matrix, Pn, as the data matrix, or more precisely, Pn transpose is the data matrix. Then this is nothing but the covariance matrix. So, for example, this is the matrix P6, and each row is a partition. But we consider this, or this the transpose of this matrix is the data matrix. And then we consider the covariance matrix, that is this matrix. And what's the meaning of these entries? If the name is a similitude matrix, I named it that way because the numbers measure how two partitions are close to each other, or how similar two matrices are. So this is like a 6 0 0 0 0, and then 6 0 0 itself, and then the number is high because of the reason is the two matrices are the same. And this number 30 represents 6 0 0 0 0 inner product of this matrix, this okay, not matrix, but this partition vector, and then this partition. Okay, and then because they are similar in some way, we have a high number. But this number is small because this measures the relation between 6 0 0 0 0 and then 1 1 1 1 1. Okay, then the inner product is small because in some sense they are different. Anyway, so that's the similitude matrix. Now, if you consider PCA, then we have to diagonalize this, but we don't need to know all the eigenvectors. Roughly, the entries measures how much two partitions are similar to each other. I explained this. And then the rows and columns are indexed by partitions. And then, we are interested in the eigenvectors. In particular, the largest eigenvalue, and then the corresponding eigenvector is the first principal the vector. So let us consider this vector V, which is the eigenvector, which is an eigenvector of the largest eigenvalue of this matrix Yn. So if you consider PCA, this is just the first principal the direction of the data set. But if you calculate this number, this eigenvector and the coordinates, then the coordinates may be different. There are infinitely many eigenvectors and etc. So we have to normalize the coordinates in a certain way. So let me do, and then the next thing is related to that kind of normalization. So first we can choose a positive eigenvector, the eigenvector which has a positive entries, positive coordinates, and then find out the maximum coordinate and the minimum coordinate. Then just scale the other coordinates like this for each partition. And then to make it a reasonable size, just multiply by 100. If you don't like 100, then you could use a different number. But 100 seems to be good. It looks like a score or some marking. So that's the definition of this R lambda. Then we'll call this number the R loading of a partition. So this measures how this partition is important in similitude matrix or in the data set for the similitude. And here the problem is how to compute the largest eigenvector, an eigenvector of the largest eigenvalue. That's a problem. But there is a very efficient algorithm called the power iteration. So the algorithm is simple. So choose one vector. It can be a random vector, but we may choose 1, 0, 0, 0, 0, 0 as the first standard vector as the initial vector. And then calculate this multiplication and then normalize it. That's the next vector. And then you apply this inductively. Then the limit is known to be an eigenvector of the largest eigenvalue of this matrix, a symmetric matrix Yn. So this power iteration is a well-known method. Rigorously, we need to check some conditions to make sure that this limit exists. But in our case, it seems that that's automatic, so we don't need to really worry. I mean, this needs a proof. But in our case, this algorithm works well. So here is an example. When n is 6, if you compute, then V0 was the standard vector, and then V1 is this, and then clearly after 6 iteration, the vectors do not change if you truncate at the fifth decimal, so it converges very quickly. So we can take this as the limit, then this gives us the eigenvector of the first, the largest eigenvalue. Then by normalizing, we get this R loadings. Then as you can see, the first partition, the 6, 0, 0, 0, 0, has a score or R loading of 100. And then 1, 1, 1, 1, 1, 1 has a score 0. I mean, here score means R loading 0. It's because 6 is kind of important to measure similitude, but 1, 1, 1, 1 is useless in some sense in measuring the similitude. And then generally, our loading decreases. The partition is, by the way, we fix the partitions. I mean, we order the partitions using the lexicographic order. Then it generally decreases. Actually, when n is 6, the order numbers are decreasing. But in general, that's not true. Sometimes there may be some flavor. But generally, the numbers are decreasing. Okay, this is the notion of R loading. But if you consider the PCA, then we are just computing the first the eigenvector of the largest eigenvalue, and then these are directly related to the principal components. Now, so far we thought about similitude. Now the opposite can be also considered, the difference between two partitions. So we consider this matrix Zn. So it's defined, the entries are defined in this way. So literally, it measures the difference between two partitions. So we take the difference and then take the sum. So lambda is a partition and mu is another partition when we are taking the sum of the differences of the coordinates. And the matrix will be called the difference matrix of the set of partitions. It's the kind of the opposite of the similitude matrix. And then this definition is motivated by a kernel method. What's a kernel method in machine learning or in data science? It embeds a data set into a different space of a higher dimension. So in like a smaller dimension, the data set doesn't show any clustering. But if you embed the data set into a higher dimension, sometimes you see a separation of the data points. So that's kernel method. But yeah, the idea is similar here. So the idea is the partition 60000 is now replaced by this 11-dimensional vector. This was a 6-dimensional vector. Now we have this 11-dimensional vector. So we are embedding these data points. The next one is 510000. This is embedded into 11-dimensional space. Then the vector becomes this vector. That's the basic idea. But by construction, this matrix is already symmetric. And then the entries measure how much two partitions are different from each other. So on the diagonal, we see zeros because one partition is not different at all from itself. So we have all zeros. And then we have 10 here because 6000 and 11111, they are quite different. Okay, that's the idea. And then for this symmetric matrix, again, we consider an eigenvector of the largest eigenvalue because that eigenvector will give us the direction of the largest variance. So that's the idea. So again, the difference matrix is symmetric. And consider an eigenvalue of the largest eigenvalue. Then they will lead us the definition of B loadings. The previous one was R loadings. Now B loadings. Yeah, I mean these the R and B are coming from red and blue, and R and B is also some represents some genre of music. Anyway, it's easy to remember, so I chose R&B, red and blue. In any case, I will define B loadings. Yeah, literally, it's I'm like consider W, and then it's an eigenvector of the largest eigenvalue of the difference matrix. Then you can choose the eigenvector with the positive entries. And then find out, I mean, that could have been the definition, but again, you can choose different eigenvectors, and then the numbers may become very small or some kind of variations. So we do normalization. So find out the largest coordinate and the smallest coordinate, and do some scaling like this. And then B lambda is called the B loading of a partition lambda. But it's like the PCA. We are trying to find out the direction of largest variance, and then we want to see the contribution of each partition. And how can you compute the B loadings? Again, we may use the power iteration. So choose the standard vector, then just calculate this again and again. And the limit exists. It needs some verification, but in all examples, it exists. Here is an example. When n is 6, we have these vectors. And it took a little bit more computations, around 10, 11, 12. All the coordinates are almost the same, meaning that it's converging relatively quickly. Okay, so we have this eigenvector, and then B loading can be calculated immediately. Then, interestingly, or in some sense naturally, the partition 6, 0, 0, 0, 0 has 100. B loading is 100. 1, 1, 1, 1, 1 has 100. But then where is the 0? 0 is in the middle. And then it turned out that it is 3, 2, 1. 0, 0. Yeah, and then it does not really decrease uniformly here. Some big number is here. That's right. But if they occur like as a pair, like this, so 1993 here, another 1993 is here. As you can see, they appear as pairs. But n equal to 6 is a pair, but that's right, yeah. They always occur as a pair like this. So that's a very interesting, that's an interesting phenomenon. So can you imagine the relationship between this partition with 1993 and then another partition mu 1993? What can be the relationship between lambda and mu? The partition 6, 0, 0, 0, 0, and then 1, 1, 1, 1, 1, 1, both have B loading 100, and then this has B loading 0. And then they appear as two partitions have the same B loading. In general, we observe that if lambda and mu are conjugate in Pn, yeah, that was the kind of the answer. If two partitions are conjugate to each other, then their B loadings are the same. This is the observation. We have not proved it yet. Of course, 3, 2, 1, 0, 0, 0 appeared just once. So it means the B loading is 0, and then there is only 1, 0. The reason is the conjugate of a 3, 2, 1 is itself a 3, 2, 1. So it's a kind of a natural thing. I mean, it's like a comparable, consistent. Okay. By the way, this is just observation. Again, we have not proved it yet. So all these things should be proven rigorously. But today's purpose is to make data scientific observations. And we are interested in Kronecker coefficients. So definitely we have to consider triples of partitions. So let us define loadings of triples. So for a triple of partitions, we'll write G of t as a shorthand, and it's not really simpler, but as a more convenient way of writing the discussion from now on. So we'll use this notation. And then when you have a triple of partitions, we define R loading of the triple by taking the sum, simply the sum. That's the R loading of the triple. And likewise, B loading of the triple is the sum of the B loadings of each partition. So it's simple. Any questions so far? Do you have any question? Okay, then what are we interested? First, let us look at distribution of loadings. Distribution of loadings. So first, R loading. Then what kind of distribution can you imagine? Yeah, these are the histograms of R loadings of the triples. When n is 15 and 16. Even if you sketch it, if you consider other values of n, the pictures are all the same. So we have these pictures. Then clearly, we can say that, or we can make a conjecture that the distribution of the R loadings of the triple of partitions is a normal distribution. Actually, here you see this curve. We did curve fitting. And then this is really exactly the curve of the normal distribution. So actually, it seems that this conjecture is true. So somehow our loading gives us normal distributions. Then we have a B loadings too. Then what do you expect for B loadings? B loadings. What kind of a probability distribution do you expect? Now, the picture is this. These are the histograms of a B loadings. Then we have this. So these are different. These are not normal distribution, but they are. Again, this is the conjecture. The distribution of the B loadings is a gamma distribution. And then indeed, you see this red curve here. This is coming from the gamma distribution. And it seems that this conjecture is true, at least for these examples. But even if we generate other examples, we see similar pictures. As a reminder, a gamma distribution has this probability density function. It's polynomial and then exponential decay. And then gamma appears as the normalizing constant. Okay, so that was interesting. But yeah, our main interest in the beginning was this. And then let's see if we get anything useful out of these considerations. So consider R loadings for 12 and 13. But of course, you can increase the number, but as an example, 12 and 13. Then the histogram is like this. Histograms are like this. When you separate the region by color according to the zero or the being zero or non-zero, according to the Kronecker coefficient being zero or non-zero, then you see these histograms. Here, red represents the case when the Kronecker coefficient is non-zero, and blue represents the case when Kronecker coefficient is zero. Then these two regions are separated, but not quite. I mean, there are overlaps, and also there are some separation. but the separation, we may say, occurs somewhere here, or somewhere here. Yeah, or yeah, there are some small red part here, so somewhere here. So this much is 100% 0. The blue is corresponding to the case when Kronecker coefficient is 0. So the separation is not very clear, yeah, or not that great. But the picture itself is very interesting. But in order for our, if you consider our purpose, yeah, then it's less useful. But B loadings is much better. So the pictures, the histograms look like this. So here, good thing is, so there are overlaps, but clearly the red part is skewed nicely, and the separation occurs, vertically, of course, the separation you see, but vertically, yeah, this much is automatically non-zero because it's purely red part, and again, this much. Yeah. Fortunately, yeah, there is a peak here, around here, and that is close to this borderline. Then how can we use this information to determine, not completely, but in order to get some information about this separation of the Kronecker coefficient being 0 or non-zero? So remember that it's difficult problem, but these histograms suggest once we know this point, or this point, then we can automatically cut out this much. We'll automatically have non-zero Kronecker coefficients. Of course, this is not perfect, but if we consider the difficulty of determining these coefficients altogether, then yeah, this may be a very useful information. So let us do that. So again, the idea is if we look at the values of B loadings, then the graphs look like this. So again, we are sketching the graphs of 10 for n equal to 10, 11, 12, or 13. Then these are like this. And this point will be important. Yeah, the pictures are all similar. These points are important because the histogram is like this. And then if you cut along this along this line, then this much in the histogram will be cut out, and then automatically those parts will have a non-zero Kronecker coefficient. So the point corresponding to this is important. So that's B star. B star is minimum of B of t, B loading, such that Kronecker coefficient is 0. It's the minimum. It gives us the borderline, and so that's the definition of a B star. So it implies that if it gives us this, if B loading is below this borderline B star, then we should have automatically non-zero coefficient. Okay, so that gives us the importance of this number. And once we know the value of the B star, then automatically we obtain sufficient condition for the Kronecker coefficient being non-zero. So remember that at the beginning we had a necessary condition. That condition is very mild, but here we are having we have found a sufficient condition for the Kronecker coefficient being non-zero. Of course, we should be able to calculate B star, but as soon as we know the value of this B star, then we obtain a sufficient condition. And this value can be used very effectively. So for example, if we have this triple, now one can ask if G of T is zero or non-zero, then you can use some computations in representation theory and algebraic combinatorics to determine if this is zero or non-zero. That's the usual way. And it takes time. By hand, it's impossible or almost impossible. You have to spend like hours and hours to compute that. But by computer, you can use it. But the computer algorithm uses representation theory and combinatorics. But here, because of our analysis, of using this B loadings, you can compute the B loading of this triple easily, and then you get 41.07, and then if we again once and for all you compute the value of B star, then the value is 44.18, about 44. So this is less than 41. I'm sorry, the other way around. So 41 is less than 44. So we immediately conclude that the Kronecker coefficient is non-zero. So in this way, this value B star can be used effectively. So when n is 20, there are about 250 million triples. So when n is 20, the size is not small. Size of the data set is not small, 250 million. So among them, about 78 million satisfies this condition. So it is about 32%. So you can determine the Kronecker coefficient being non-zero for about 32% of the triples. So this is quite, quite effective. Okay, then the problem is now how to compute these numbers B star. Of course, we use computers. Then I obtained these numbers. So at the beginning, there is some fluctuation, but later the numbers become, in particular around here, numbers become very similar. I mean, the fluctuation is very small. And when you and you can compute the triple when you obtain these the value B star. Then when you have triples of 3, 6, 9, 12, the lambda, mu, and nu are all the same. So here, lambda, mu, and nu are the same. So we can make a conjecture that B star is obtained when at least two of them are the same. In particular, when n is a triple of 3, all 3 partitions are the same. So that you can make this conjecture based on this table. So we could compute until up to n equal to 20. And if we want to increase this n further, then now it's very expensive, because when n is 20 already we had 250 million triples. So you can imagine that it becomes more and more expensive. But if we assume the conjecture, then we know that when n is a multiple of 3, all 3 partitions are the same under the conjecture. So with that condition, we can compute further. Then B star is the values of B star are here. We can compute the value of B star under that condition, under the conjecture. So again, there is a small fluctuation, and then the size of the fluctuation seems to be decreasing. So it's the values are around 44.5. But can we say that B star converges to some number and converges to some number when n goes to infinity? Then the purely data scientific way, there is no possibility to answer the question. So this is the moment. So it's not clear. This is the moment we need the representation theory again. So far, if you think about my presentation, we have not used any representation theory. In the beginning, we defined what Kronecker coefficients. Of course, okay. When we generate the data sets, we use the algorithm from representation theory. But we could not avoid talking about representation theory. Now, when you have to answer this kind of a question, then we need some understanding from representation theory. So we have to go back to representation theory. But still, and the observations made in this talk need rigorous proofs. Again, the proofs should come from representation theory, and other things are independent of representation theory. But anyway, today's talk is a data scientific thing, and then rigorous proofs are needed. And still, another aspect is that today's method is linear. So there were no nonlinear methods in interpretation. All our interpretation methods was linear. Some nonlinear method may be needed for further analysis. So in order to see more separation and more information about the Kronecker coefficients data scientifically, then probably we need some nonlinear methods. And the machine learning result presented in the first part, we saw 98% of accuracy. That means if we apply the proper nonlinear methods, then we can see much more than today's results. So it's not the end of the story, but it suggests that we have to apply other methods to understand Kronecker coefficients better. Okay, it's about the time, and then that's all for today. Thank you.